When we consider the homogeneous spheroid, let's consider one example of an inhomogeneous. This particular density distribution is of interest, with M again being the label of the homoids, which can approximate to the bulge density. Here, A naught is the core radius, and E is the eccentricity. We can calculate the circular velocity that this density distribution would give by knowing the potential. Well, calculating the potential, again, results in a complicated integral that gives some special functions as a result, where f and e here are incomplete elliptical integrals, and k is given by this quantity. That looks a bit complicated. In fact, a spherical approximation is not a bad approximation for the bulge. If we return it to the general spherical density, the model with alpha equal 1 and beta equal 4 is called the Hernquist model, which leads then to this density, which turns out is a good approximation for moderately spherical bulges. Now, the mass of this model is given by the integral of the density, which can solve in pi to find this expression. So that's the mass of the Hernquist model. Now, the gravitational potential, we can integrate, find this expression. Now, the last component would be the potential of the disk. Now, for an axisymmetric system with the density depending on radius and the vertical coordinate, the Poisson equation can be written in this form, only as a function of radius and z. And because the material is very flattened, then the variation in z is much smaller than the variation in r. That means that this term dominates, and then we can exclude the radial term. We approximated the potential then only by the z term in the Poisson equation. So this implies that the vertical variation of the potential at a given radius depends only on the density distribution at that radius. That means that we can split the solution of the Poisson equation for a thin disk in two steps. One, we can approximate the thin disk by a Dirac delta and determine the potential in the plane of the disk. So phi of r and 0 here would be the vertical direction. And then we solve for the vertical variation. At each radius, we solve this equation to find the vertical variation of the potential. And by superposition, the potential is the sum of both potentials. An application of that would be the exponential disk. So several galaxies have a luminosity profile that is fit by an exponential function. Now, for an exponential disk, the potential in the midplane is given by this expression, where y is this quantity, r over 2rd, and I and k are modified Bessel functions. The corresponding circular velocity is found by taking the derivative of this potential in r equals 0. And here you have the circular speeds of an exponential disk. That's the one with the full line here. The dotted curve here is the potential of a point mass with the same mass as the disk. And the dashed line is the potential of a spherical body for which the mass of each radius is the same as the mass inside the radius for the disk. Now, if we put it all together, NWF potential for the dark halo, a Hernquist bulge potential, and an exponential disk potential combined give a reasonably accurate galaxy potential. And this figure here gives a contribution of each one of these quantities for the circular speed. This is the contribution of the bulge, contribution of the disk, and the contribution of the halo. And this is the total circular velocity curve. It's the halo that contributes most.